press the go live now. Hello, everybody. This is a Qualia structure seminar, and today's speaker is Dr. Tadahiro Taniguchi, who has been proposing this emergence of symbolic communication in Japan, and he has broad knowledge across linguistic and development and robotics and AI. And this is going to be quite an interdisciplinary talk. And he's going to make it accessible to many of us, hopefully. We'll have some question time at the end, but also we'll take a break after 25 minutes after the start, for 5 minutes or so. Please go ahead.
Thank you for introduction. Okay, can you see my slide?
Exactly. Yes.
Okay. Well, thank you very much for inviting me, the Professor Tsuchiya Sensei, the Professor Moriguchi Sensei. So I'm Tadahiro Taniguchi from Ritsumeikan University. So good morning. I'll be talking about symbol emergence in robotics and the collective predictive coding hypothesis. So the later part, collective predictive coding hypothesis is a kind of a new proposal from me, and it's actually the unpublished topic, but I think that it will be exciting for you. Okay, so let's get started. So this is my profile. I was originally from the mechanical engineering field, but afterward I moved to the information science, and I'm working for Ritsumeikan University now, and I also working for the Panasonic Corporation as well. My research topic is about machine learning and cognitive and developmental robotics, symbol emergence robotics, and language acquisition as well. So maybe we should start. So maybe there is many various audience here. So let me show some videos to give you some flavor of our research. So these are the videos about our research about symbol emergence in robotics. And this is a video about unsupervised lexical acquisition and the spatial concept formation. And this is a video for the about the application to service robotics, multimodal object categorization, and imitation learning and reinforcement learning, and multimodal world modeling, and so on. So I want to talk about some of the details of this later in this talk. But I would like to mention one thing. So all of these experiments are using probabilistic generative models, partially at least. Okay, so I'm a kind of researcher conducting this kind of robotic experiment. So you may think that, oh, he is a robotician, and he may be interested in the robotic applications. But to be honest, that's not true. So what I'm interested in is computational understanding of mental development. And it's from behavioral learning to language acquisition. Sometimes people mention such kind of entities as low-level cognitive capabilities and high-level cognitive capabilities. The human children acquire many skills, physical skills, and concepts and knowledge, including language, through physical and social interaction with their environment. So we would like to obtain an understanding of the computational process of mental development and language acquisition. So this kind of approach is called constructive approach sometimes. So that's developmental robotics and symbol emergence in robotics. So first, let me share my view about the autonomous system or agent. Let's start with this figure. So an agent here is in an environment. The agent has a sensor motor system and connected to the real world environment using sensor and motor information. Based on such sensor motor information, many kinds of cognitive capabilities, including motor skills and perceptual categories, the planning capabilities are gradually acquired by the agent. They are ranging from low-level cognitive capabilities to high-level ones. And note that some sensory information comes from other agents. Sometimes this kind of information interaction is called social interaction. So based on such a social interaction, the agent learns to, for example, estimate others' intention and also acquire language, and that can be called a symbolic system as well. And actually, the language includes syntax, lexicon, phonetics, semiotics, and pragmatics, and so on, super complex, okay? The point is that even high-level cognitive capability, including language, is organized in a bottom-up manner based on sensory motor information. So, and make things more complicated. So, all of them has a. So, in addition to that, also they are mutually dependent. For example, perceptual category affects lexical acquisition, and lexical knowledge affects perceptual category formation, and so on. So we should, and actually in most robotics research, these kinds of cognitive capabilities are developed independently by the engineers and implement them as a kind of modules, fixed modules to the robot. But we should think about this kind of mutual dependencies and the kind of the organizational process as well for understanding human intelligence, human cognitive system. So from this view, I want to have a discussion about what is intelligence. But this might be a very naive, rough discussion, but though the huge progress that has been made in development of AI, as you know, the view of intelligence itself is often kept to be simple, I think. So most of the AI technology are still limited to a kind of functions that are single-purposed and task-oriented, like visual recognition and automatic speech recognition, and so on. So this is just a function. So in contrast, human children developed using its own sensor motor experience as an autonomous cognitive system. And the cognitive system is not single-purposed and not task-oriented. It performs many tasks using acquired knowledge. So, and such knowledge is acquired through the kind of self-organization of sensory motor information flow. So, such a learning process leads them to not only acquisition of physical skill, but also to language acquisition. So I have this kind of view about intelligence, and intelligence is a kind of a cognitive dynamics, I think. So, okay, this kind of view, I think this kind of view is very consistent with a recent popular view of free energy principle, predictive coding, and the world models, and so on. So I love this kind of, maybe many of you may know these keywords, and I like generative view of cognition like this. So I'm a researcher in using constructive approach. So I want to build an artificial system with this view. That's an important point of our work. So from this viewpoint, so so if we described this kind of generative view in a as a simplest manner, this is kind of abstract description of the generative view. The cognitive system having many sensory or motor information and observations, and have some internal representations. With this internal representation, latent variable Z, the system tries to predict the observations. And from the observation, the cognitive system like to predict, infer its latent variable. It's a kind of recognition. So this description is often called probabilistic graphical model. It's a diagram-like description of probabilistic generative model. Okay. So the following this view, we have developed many kinds of constructive models. So let me show a video, one of the video. So the robot moved around and grasped the object several times and obtained haptic information. And shook it to obtain the auditory information. And look at it from different directions and obtain the visual information. So actually, this is a bit of old work, almost more than 10 years ago. Our collaborator conducted this research. And to integrate such kind of multimodal information, so we can use this kind of generative model. This is a multimodal latent judicial allocation. This is a kind of a clustering method for multimodal data. So by integrating the multimodal information, visual, auditory, haptic information, the robot could form object category like this. These are the object category categorization result. So actually, this kind of clustering task can be performed using the modern generative models like multimodal VAE, variational autoencoder, and so on. But I want to say is that actually the robot can form these kind of human-like categories. Just try to improve the prediction capability. And by starting with real-world embodied sensory motor information is a key of our research as well. So actually, we are using this kind of generative model. We use this kind of generative model, and in other words, latent variable models. So some of you may know the machine learning theories around the AIs. So there is a very famous three divisions of machine learning method: supervised learning, reinforcement learning, and unsupervised learning. So the graphical model, the probabilistic generative model, is often used in unsupervised learning. But actually, supervised learning can be described like this, and this is also can be interpreted as from the viewpoint of a generative model. But how about reinforcement learning? The reinforcement learning is a kind of method for decision making, and the optimization criteria is to maximize the future reward. But actually, so during this decade, the idea of control as inference became popular, widely known. So actually, the conventional many types of reinforcement learning formulation, the mathematics, can be transformed or can be translated into the probabilistic modeling and inference. So mathematically equivalent way. So in some sense, we can say that predictive coding and inference is a very general way to model the system, cognitive system. So we might explain this view with introducing our previous work about a special concept formation. So, and in previous slides, we showed the research about, I talked about the research about the object categorization, but also a special categorization, the place categorization and the special concept formation is important for us. So we develop, so what's important for robots that live together with us and provide services to us is not only object categories, but also the knowledge of places. For example, please go to the kitchen and bring me a pet bottle or something like that. Is a very popular task in service robotics, and that also involves knowledge about the kitchen. So what is the knowledge of kitchen? Maybe you can imagine where is the kitchen and what is in the kitchen. So refrigerators, the toaster, and the knives, and so on. So from this viewpoint, we think special concept is also a kind of is also based on the multimodal information. So we developed a machine learning method called SPOCSLAM. So online simultaneous spatial concept formation and localization and mapping. This can form a map, find a cluster of positions, and discover words representing places from speech signal simultaneously by integrating the multimodal sensory motor information. This is the overview. This looks very complex, so you need not fully understand this diagram. But please look at this. The robot has 4 kinds of observations: the visual information, and the speech signals, and the distance sensor information, and its action sequence. So by trying to predict this information, the robot will infer latent variables, its positions, and what is a map, and the cluster of positions representing some kitchen or toilet and so on. And also try to find the vocabularies, word list from speech signals, and combine them as a kind of integrative concept, CT here. So this is the example of the experiment. The first robot move around in the house, in the building, and the robot, at first, the robot did not have any maps and cannot estimate its position. But gradually, as the robot form map and estimate the position, at the same time, sometimes user or people talk to the robot, and oh, you are walking on the corridor, or you are visiting a toilet, or this is a copy room. You are in front of the elevator, or something like that. So from such kind of speech signal, the robot try to find the words, lexicons. And at the same time, the robot observe visual information. And the robot try to integrate the positional information, visual information, and linguistic information together, and form spatial concept. And without kind of any, a priori, some programming about what is the location and the kind of the list of words, and so on, the robot can form this kind of knowledge in a bottom-up manner from the real-world information. Okay, this is some of you may think, oh, but this is just a clustering. So this kind of concept formation is why this kind of concept formation or modeling is important. I don't know that, such kind of things. But notably, the cross-modal inference is very important keyword here. For if the robot, the cognitive system can model the joint distribution, kind of multimodal, the distribution of a multimodal information, the robot can calculate and infer from one information, sensor information, to other information. For example, position to speech language, position to language. For example, if the robot visit a certain place, the robot can tell oh, this is a toilet, for example. So by inferring the one variable, by inferring the word variable, latent variable, from the positional information. So we can set many directions for speech to position, like the robot can estimate its position by hearing, oh, you are in the toilet, and so on. And image to position, and the position to image, image to speech language, speech and speech to image, and so on. Actually, the robot, this is a single system, single cognitive system, but cross-modal inference can give the robot many kinds of functions. That's an important point, I think. In addition to that, but these stuff are almost about the perception. How about the planning and the action? That's a domain that's often dealt by reinforcement learning or planning studies. As I said, actually, the reinforcement learning itself is theoretically can be considered as the reinforcement learning can be considered as the probabilistic inference as well. So I don't how to say I shouldn't get into the mathematical detail in this talk, but we can consider this graphical model, generative model of SPOOK-SLAM as a kind of extension of POMDP, partially observable Markov decision process. So as you may know, the Markov decision process is a kind of theory for reinforcement learning. And if I make story short, long story short, this is a kind of the extension of MDP. And actually controlled as inference approach can be utilized. And if, for example, how to say, by if the system model the sensor model information, if the robot, if the system try to infer the future sequence of actions to observe the future observations about the goal. So maybe this is complex, but such kind of Bayesian inference of future action sequence, it can be considered as reinforcement learning. And actually, without any additional equipment, this system can perform some sort of the planning, reinforcement learning as well. And actually, oops, sorry, maybe sound is too big. Sorry for the sudden play of the video. And, but what I want to say is that we have been conducting theoretical research in the simulation environment, the laboratory environment, But we are also trying to implement these kind of methods into the service environment as well. But to be honest, to be honest, 80 or 90% of this robot is, how to say, is operated using a very conventional robotics approach. Just a part of cognitive system of the robot is built on this kind of idea. Yeah. I still have a time before the break. Okay. See? Okay.
Yeah, so it's actually quite a good time because in 30 seconds, it's roughly the planned break. So should we take a break now?
Okay. Yeah, it's yeah, relatively good point for me as well.
Okay. Then can I share the screen now so that I can show the
Okay.
timer? All right. So okay, we'll come back in 4 minutes and 50 seconds. Thanks, Taniguchi-san. This has been very inspiring and very interesting and also easy to understand as well, even for us.
Yeah, I will take off as well, take a break as well.
Okay, so Taniguchi-san, when you are ready, please.
Yeah. Thanks. So, reboot. Okay, can you see my slide?
Yes.
Okay. So, welcome back. So I'd like to continue my talk. So as you saw, so we developed many types of integrative cognitive models that are based on probabilistic modeling of sensory motor information. And actually, this is the graphical model of SPCO-SLAM I introduced in the previous slide. And this is another model, MMLDA, and this is another model. And actually, I and other collaborators and related researchers built this kind of very complex models. But as you may notice, it's very tough to build this kind of system by a single PhD students. Actually, this model involved visual recognition, audio information, and audio processing, and natural language processing, and self-localization, and so on. And actually, these modules are implemented by a single one PhD students. I think it's a super tough job for machine learning people and robotics people. So, but we noticed that when we build this kind of generative models, so these are just a composition of elemental probabilistic generative models. For example, this part is SLAM, and it's a Gaussian mixture model for clustering, and this is for multimodal categorization, and this is a speech recognition system, and so on. So if we have a kind of framework that can combine probabilistic models into a single probabilistic model, and that allows, if such kind of framework allows us to easily implement an inference method, so that will be very helpful for future research and development. Then we propose a circuit framework. And the idea is very simple. So two modules, this is a very kind of basics of the machine learning, but two modules can be decomposed. So by one variable usually. So if we, after this decomposition, the inference process can be decomposed into inference in the internal inference and some sort of the external communication between modules that can very naturally approximate the exact inference process. So this is an example. So in the paper, we show that using this kind of method framework, we can easily combine variational autoencoder, Gaussian mixture model, and latent Dirichlet allocation, and automatic speech recognition system, for example. This is a total graphical model, but this can be decomposed like this. And by just using the softwares, pre-implemented softwares about these modules, we can build this kind of very complex models. So I think that this kind of approach is opening the door to build a more complicated and ambitiously human brain scale, can say, integrative cognitive system. So this is a kind of position paper published last week, actually. So we collaboratively wrote this paper, a whole brain probabilistic generative models toward realizing cognitive architecture for developmental robot with AI people and robotics people and the brain science, neuroscience people like Doya sensei and so on. So this is the kind of the future challenge as well, I think. Okay, let me move on to the kind of next topic, a bit different topic. So let me revisit this slide. This is actually the first slide of this talk. So I mentioned the cognitive development in this paper, but there is another figure here. So this figure, what is this? And this is a figure of symbol emergence system. Actually, the difference between the developmental robotics and the symbol emergence in robotics is related to this figure. Symbol emergence in robotics is a kind of constructive approach to not only single agent, a human child development, but also the symbol emergence system. This is the this is a social system. So let me explain this theory. So what is symbol? That's a question. So we use symbols in our communication, but a symbol is not the kind of just an entity inside our brain. That's the kind of tools or signs in the communication as well. So but that's based on the human, category or concept and so on. Anyway, a human forms the category and the concept in a bottom-up manner, and through the embodied physical and physical interaction with his or her environment. So, so such elements formed, category and concept are formed in his or her cognitive system, become a basis of human symbol system, symbolic communication. And such kind of category can be formed without any linguistic information, as we saw in the robotic experiment as well. This is a kind of internal representation. So even though concepts or category is just what we have internally. So using this kind of concept, people can describe their situation and desires using many kinds of signs like language. So they can also interpret the signs using the formed concepts and the categories as well. This process gives them very primitive capability of semiotic communication. But in this way, the symbol system used in the community is gradually organized in the community. The organized symbol system should be shared among the community to enable the participants to use the symbol system and communicate with each other. So if the agent does not follow the rules of the symbol system, they cannot achieve the good communication. So, so sharing a symbolic system means that each agent should use and interpret the signs in the same way as others. To join this community, each participant has to give up a certain amount of their degree of freedom in expression and the way of interpretation of sign by following the shared symbol system. So the shared symbol system, this symbol system involves vocabulary, syntax, and so on. So this gives a kind of top-down constraint to every agent's way of communication, and actually perception and action as well. So we call this emerged the symbol system, emergent symbol system. So actually, the current most of AI, our research and most AI-related studies just treating the dynamics of these symbol systems very in a static manner. So they assume the relationship between words and phenomena and words and object, label and object fixed usually. This is very much related to cultural aspect of language. So such dynamics of symbol system itself should be taken into consideration. Okay, so our study is moving towards the constructive studies on language evolution and symbol emergence, this layer as well. But how can we model and theorize and reproduce and grasp the symbol emergence in society? That's the question. And historically, many studies in artificial life and complex systems and artificial intelligence were conducted about symbol emergence and language evolution. But important points are still missing. So I think these requirements are important. So especially the clear theoretical basis of the optimization in terms of the agent's adaptation to the environment. So what is the optimization criteria of organizing this? And how can help the agent's behavior? And so on. Then a predictive coding comes again. So maybe this will be a complex and the time is limited. Maybe I will skip some part. But the important change of view is this. So we published a paper about this model. We can consider symbol emergence as an interpersonal multimodal categorization. So making a story short, so actually if we regard the two agents as a single multimodal categorization system, the graphical model becomes like this. But by using circuit approach, we can divide this graphical model into two parts. And but to infer these latent variables, we need some sort of communication between two nodes. So actually, if we apply a method called Metropolis Hastings, that is a kind of Markov chain Monte Carlo. So we found that a very natural naming game, language game, can be derived like this. So in this scenario, the robot agent A observes the object and try to give a name, but the robot agent B has different knowledge, and the robot can judge, the agent B can judge if he accepts this name or not. So this is a very, natural or conventional view of naming game, kind of language game. So then if, in this case, if the robot follow this probabilistic rule, so probabilistic rule, the naming game become equivalent to the Markov Metropolis Hastings algorithm. We found that. So this is just a comparison between the likelihood of the new suggested word calculated based on listener's belief. And this is the likelihood of the previously believed word. Okay, so the listener just compare which word is better for him, and probabilistically determine if he accepts or not. So, but this is a kind of overview of naming game. But importantly, this naming game is mathematically equivalent with the inference process of this kind of integrated system. Okay, so we conducted the experiment, and actually the system two agents observed the same object from different viewpoint and try to perform the clustering, categorization, and playing the naming game simultaneously. So we found that they could formed. They could share sign system. And also that improves the categorization capability as well, performance as well. So naturally, we could extend this idea to more multimodal settings. And we found that shared symbol could even help other agents who do not have a sufficient sensory system to form categories. For example, if another agent does not have a haptic system or visual system, so other agents' categorization result can help the others' categorization capability. And another new idea can be derived. So that's the interpersonal cross-modal inference. Actually, the system combining two agents can be regarded as a single probabilistic generative model in this theory. So in this model, another agent can infer the visual or haptic information from the word another agent generated, and this is theoretically equivalent to the cross-modal inference in the multimodal categorization. So this tells us semiotic communication can be interpreted as interpersonal cross-modal inference. It's a kind of cross-modal inference. Okay, that's the story. And this kind of findings, led us to a new hypothesis. So that's a collective predictive coding hypothesis. So symbol emergence may be a phenomenon with which people perform predictive coding as a collective system collaboratively in a decentralized manner. So, usually we tend to think our knowledge is just inside of our brain, but we people can work together, sharing the symbol system. So in other words, symbol system are combining our cognitive system in this way. That's a kind of collective predictive coding hypothesis. Okay, that may be a take-home message about this talk. Symbol emergence is equivalent to the collective predictive coding. In addition to that, another maybe take-home message or question. So in this talk, many functions are realized as probabilistic inference, action planning, categorization, perception, and communication as well. So to what extent this kind of idea is general? That may be a open question as well. So, okay. So almost that's all. So thank you for listening. That's all of my talk. Thank you very much.
Thank you very much. Great talk, and it was quite accessible and also quite insightful. I'm pretty sure that there will be a lots of questions. And I want to first invite any questions from many young people, either in the Zoom, through chat, or maybe raising the hand, or also YouTube comment as well. But if not, then maybe we can, we senior people can start questions. But maybe before others raise hand, then I'll just ask first question then. So about that, your model, in general, are there usage of the recurrency of the activity, or is it generally like no? Yeah,
that's a very important question. And actually, the clustering tasks, categorization tasks, we didn't assume the recurrency and the temporal aspect. But this planning and the special concept formation, in this model there is some sort of recurrency but just a kind of just a Markov process the latent variable is has multiple property.
I see.
Maybe. And
so if you were to sort of realize this system in a physical manner, then will it become like a almost feed-forward system? Or will it have a sort of the ongoing dynamics, spontaneous dynamics if you completely turn off the input?
That's a very good question, and that depends on the system. To be honest, for example, this model involves a graphical model of POMDP, partially observable multi-decision process. So usually the world model, recently gathering attention. The world model is based on the POMDP. That is usually implemented based on the recurrent neural network, and it has the spontaneous dynamics. But relatively, in our study, we haven't studied or considered the spontaneous dynamics itself, not so much.
I see. The reason why I asked this is to some extent to link with your work with also the relevance to consciousness studies, where many people and also many kind of neural activity based type of study implicates that the recurrent activation is somehow key to understand the consciousness. And that's one thing I wanted to ask about your network.
That's right. That's actually what I thought when I read your book last night. So maybe the consciousness, the discussion about the consciousness put much emphasis on the kind of internal spontaneous dynamics, I think, to my understanding. So, but that's actually what we are missing now here in this model. And but also I say very related research to us is maybe Jun Tani in AEST and Tetsuya Ogata in Waseda. So actually, theoretically, so this kind of POMDP based model is very much connected to we can have the very general concept, and they put much emphasis on the spontaneous dynamics of the recurrent neural network, to my understanding. And actually, I think so. That's a kind of a bridge, and I think we can find some connection, nice theoretical connection between our research and the research in consciousness. I hope so.
I see. Yeah, in the case of Tani-san's study, Tani-san's robotics, the recurrency is also used as a sort of to realize a different kind of time constant across different levels of the hierarchy.
Right.
Yeah, longer term, more stable kind of plan is associated with a long term recurrency at the highest level, and then short term and
especially MTRNN, large time scale recurrent neural network they use.
So that kind of thing is not still built yet here.
Yeah, that's right. But from the probabilistic modeling view, so that is kind of the hierarchical modeling of time series data, and such kind of extension was conducted by many researchers for very much similar models. So I think so the merging their idea of MTRNN and our approach will be we can combine two ideas. We can integrate two ideas in the near future. That's actually our challenge as well.
I see. Okay.
That's very important.
yeah, the other thing that I also wanted to ask in terms of a global kind of question is that you have been using this unsupervised learning across many different components, but recently, one of our collaborators, Masafumi's group, has been also using similarity-based kind of unsupervised learning.
Mm-hmm.
Similarity of the patterns, or similarity of the inputs, or similarity of the objects. And if you consider that across time, that also probably extracts the stability or invariant feature of the environment. And that also doesn't rely on sort of explicit construction of the symbols or symbol manipulations, right? Have you thought about these kind of usage of the similarity or other types of the metrics to realize some a part of the robotics?
Thank you for the it's a very good question. And actually, before answering that question, I want to solve the one misunderstanding. So what we are talking about a symbol. It's a kind of a symbol in semiotics, and that's a kind of symbol in our human language. I'm not talking about the symbols of our internal system. So conventionally, the symbolism and representationalism in cognitive science, in AI, requires kind of explicit representation inside our brain as a symbol. So what we are talking about symbol is not such kind of a symbol. So we do not assume such kind of symbol system and symbolic manipulation. So what we are conducting is very much similar to such kind of similarity metric-based approach.
I see.
So try to find the statistical dependency between the different modality information. And but how to combine multimodal information and other type of information and pre-existing language processing method and so on. I think the more general theoretical framework that generalized many kinds of methods is important. And I think the probabilistic generative model-based approach is good for that. And so we prefer this approach. But I think at some point, we will find in 10 years or 20 years, I don't know, we will find kind of the generalized view governing such kind of differences, I think.
I see.
Okay, so that's pretty good, and also demystifying sort of my misunderstanding maybe that so quite unlike the really early generation of the AI, you've been using this probabilistic generative models, so that in a sense kind of get rid of the explicit representation.
That's right.
And, very different from the early computationalism or representationalism.
That's right.
Would you even say that then your approach is closer to non-representationalism or anti-cognitivism kind of approach?
More kind of similar to the non-representational or and even connectionist approach. So I think, but how to say? So I haven't successfully locating my position in the kind of historical context.
I see.
Okay. Maybe I asked too many questions, but is there any questions from audience, either YouTube or in Zoom audience? Any question is probably fine for developmental or linguistic or robotics. Maybe they were quite sort of intimidated by the breadth of the components of the talk, possibly.
Come on. Moriguchi-sensei?
Moriguchi-san? Yeah.
Yes, thanks for your great talk. I'm very impressed your advance of the research. Actually, I have heard your research from the Nakamura Sensei's categorical learning 10 years ago, like that. But this is kind of my question. So you have presented from the basic categorical learning to the planning or like more special learning. So more basic from to the more higher order research. So, but you mentioned that these capacity is interrelated, right?
Yeah, that's right. That's right.
But so you, from the developmental perspective, maybe categorical learning can be fast and special learning and planning. But do you assume that there's some this is kind of a developmental process from the basic categorical learning to the planning, or these components are, how can I say, interrelatedly developed in the single agent? So can I get to my point? So
thank you very much.
You assume that,
yeah. So that's a very important point. And what we have been trying to build is a kind of the model, kind of integrated model, to have a discussion about such kind of topic. So this is a basis. And actually, the previously we just have a kind of simple computational models that can only perform the visual recognition or very basic language learning, just modeling a sequence of words and so on. So, but when we look at the developmental process, the babies, infant can continuously build their cognitive system and acquire knowledge and so on. So the very integrative manner. So to have such kind of discussion on the computational basis, first we need a kind of the integrative computational model. So reproducing such a phenomena. And after having such kind of system covering the topics, which we are discussing, we can think about the kind of parameters in the model and what is missing. To be honest, I think in some sense, compared to the 10 years ago, maybe we had a discussion previously with Moriguchi-san, and we somehow I could made some progress, and I think I'm now just a little bit better status position to have a discussion about the correspondence between the actual mental development and this computational model. And in addition to that, for example, about the phonetic category learning and the language word discovery. So usually phonetic system it was formed before the word discovery started. In the 9 months or even before that. So I in some computation study, we found that such kind of the pre-training of phonetic system is important to improve the word discovery. But it's not a kind of solid result. So it's just an example of the experimental result. But now we can touch such kind of topic as well. So and maybe I omitted that model from this talk, but that's the point.
But I think I always ask this question, but your research is really compare the real human learning or human child development. So kind of compare your result, robotics result, to the human learning, actual human learning or actual human development. So do you compare your result to the real human behavior?
To be honest,
Not really.
almost no currently. Almost no, and just a qualitative level. Just a qualitative level. So we are always how to say we are also imagining good actual development process, and I try to get rid of the information that is not available for human children, like label data directly inputted into the brain learning system. So, but yeah, we are still at the very qualitative and the preliminary level. But as I mentioned that before, that we reached a bit better stage now. So this is, I hope this is a good opportunity to reboot the discussion with you as well.
Okay, yeah, thanks so much.
Okay, is there any further question from the audience? Or otherwise, I might ask one more question and then maybe we can move on to the more closed discussion. So another kind of perspective from consciousness research is that towards the end, you suggested this collective predictive coding.
Yeah, that's right.
I think it's quite interesting. And recently I've been thinking that the perspective of an agent is really essential for not only consciousness study but also for robotics as well. Like any kind of reward or optimization or motivation or something when you talk about, you are, I mean, not to you maybe, but some people tend to assume that there is some kind of single sustained entity that has a constant value or belief across time or across space, right? However, from the neuroscientific point of view, there's no such empirical, self that the brain or in the cognition, and rather it's more to do with a collection of the self-like kind of process or functions that they are interacting in many ways. So in that sense, your collective predictive kind of agents may be residing within one brain, and then trying to sort of communicate with them or trying to be dominate on one over the other, and then the winning one is possibly like conscious or dominating kind of narrative thing. What do you think about this kind of
that's a very interesting and great questions. And actually and when I read the discussion about the IIT and so on, so such kind of has some sort of decentralized view of the brain function is attracting me, and actually somehow this kind of approach, this circuit framework, originally these for example, this SLAM model, the SLAM model and GMM, MLDA, the ASR developed and work independently, and but have a communication between the across the modules, between the module that the circuit allows the module to have a communication between, and they work together as a single the system. So I think there is no good answer, but this kind of view can may be able to give us a connection what you are discussing and I'm discussing. And in addition, regarding the collective predictive coding hypothesis, so what's important point is that theoretically, the communication between the modules inside the brain, like a vision or haptic recognition and so on, and the communication between agents are theoretically almost same. So that leads us to some ambitious, some hypothesis that if the single agent have a some sort of self or consciousness. And the society itself, symbol system, society itself can have the similar stuff. So that's what I'm thinking about now. And maybe
without sort of that perspective or subject presence, I mean, in terms of IIT's terminology, it's called complex. They talk about the boundary of consciousness, and probably in the work of the Carl Friston and so on, he talks about the Markov blanket, right? And these kind of a concept of the boundary, if without having something like that, then you would naturally arrive at that kind of consciousness in the society or consciousness of the earth or universe. But I don't know whether that's actually either empirically observed or testable or something like that. But that's a good question for future, I guess.
I don't know as well. But yeah, if we, which is kind of just my ambition. But if we can build a connection between the IIT-based consciousness theory research and our generative model-based approach, so for a single agent, such kind of discussion can be generalized to the consciousness of society through with this collective predicting hypothesis like idea. So that's also motivate me to have such kind of discussion, think about such kind of connection.
I see. Okay, that sounds like a quite good, deeper conversation after this one. So if there is no other question from general audience, otherwise then we'll stop the streaming here. And again, I want to thank Taniguchi-san again at this point. Thank you very much.
Thank you very much.
Okay.